Hello, everyone, and welcome to the second debate of this conference. We'll start with a few ground rules. As you probably know, this is a Zoom meeting, so if you are not talking, remember to mute yourself. And after the two debaters have talked, please feel free to ask a question via the chat box by raising your hand with the reaction button at the bottom of your screen, or simply by interjecting. I'm Chloe Arson. I'm one of the co-chairs of this conference, and this is my great honor to be moderating this second debate today. So Darcy's law is an equation that describes the flow of a fluid through a porous medium. In that equation, a linear relationship is established between the flux and the gradient of pore pressure through the permeability tensor. The law was initially established for 1D fluid flow through sands. Here, the question of this debate that we are raising is whether or not Darcy's law can be applied at the scale of individual pores. Dr. Catherine O'Sullivan, who is a professor at Imperial College London in the UK, will defend the motion of this debate, that is to say, Darcy's law is meaningless for flow within individual pores. Professor O'Sullivan is an expert in particulate mechanics who made significant contributions to the field of geotechnical engineering. She's also known for her research with the distinct element method, or DEM, on which she wrote a book. Her debate opponent today is Dr. Benoit Coasne, who is a CNRS research director at the Interdisciplinary Physics Laboratory in Grenoble in France. He's a physicist by training, working on adsorption, phase transition, and transport in porous media. Dr. Coasne made significant contributions to the field of pore mechanics, in particular through the use of molecular dynamics simulations. So we will start with Dr. Catherine O'Sullivan's motion, who will speak for 15 minutes. After that, Benoit will oppose her thesis for 15 minutes. And after that, we'll have a series of questions and answers. At the very end of these debates, the audience will be able to vote on 2 or 3 questions that will be pulled out to the screen via software for which you will have to connect online. And I believe that SA will post in the chat box very soon the way to do this, and the website you have to connect to and how you log on to the Q&A system. So without further ado, Catherine, the floor is yours.
Thank you, Chloe. Hopefully I can share screen now. So thank you very much for this kind invitation to participate in this debate. I just need to hide some things. As Chloe said, I'm based at Imperial College. I think it's very important to say from the outset that I'm a civil engineer, and I specialized obviously in geotechnical engineering. But upon graduation, I did spend a small bit of time working in industry in California, looking at flow problems associated with the integrity of levees or flood embankments. And I know that the flow of water through flood embankments in the UK at the moment is posing a significant challenge to the Environment Agency, which manages levees in the UK. And one of the problems they're particularly concerned about is the fact that failures initiate around inclusions in these flood embankments. So thinking about flow through porous media at that macro scale, I can start to understand that the heterogeneity of that flow is very important, and the change in the flow regime through the flood embankments that's induced by a transition such as a culvert or a pipe going through a flood embankment that can cause significant problems at a macro scale. So I'm going to approach this talk today from my perspective of teaching seepage to master's students who are going on into industry to look at that kind of problem, to look at the stability of flood embankments, or to look at flow around excavations. And I'm also then going to draw in some of the recent research we carried out, both experimental and numerical, to look at flow at the subparticle scale in sand. So as Chloe said, Darcy's law is saying that there's a linear relationship between our flow rate and our hydraulic gradient. And in soil mechanics, the way we tend to write Darcy's law in the one-dimensional form is as you can see here. So we have our discharge velocity, which isn't really a velocity at all, it's a flow per unit area. But we do use the term velocity in geotechnical engineering practice to talk about this flow per unit area. We have K, which is the hydraulic conductivity. But in soil mechanics or geotechnics, we're a bit sloppy, and we often call this K, which is the constant of proportionality in Darcy's law, the permeability. But obviously, there's the true permeability is related to the hydraulic conductivity by the bulk unit weight and the viscosity. So we have to be careful about terminology. And you know, it's widely acknowledged that in geotechnics, we are a bit sloppy in terms of using that term. And obviously, I is our hydraulic gradient. And when I'm teaching, I like to remind our students that that's really a measure of how the energy in the flow is changing as the fluid moves through our soil, and a cartoon here to remind us about what that might look like. So in geotechnics, we then kind of recognize that this discharge velocity isn't really a flow, and we could correct it and say, if we divide this discharge velocity by our porosity, that's the real velocity of the water within the pore space. So this is something that you will see in textbooks for soil mechanics students. And as I've said already, for 15 years now, in fact, more than 15 years, I've been teaching a course that's solely dedicated to seepage and consolidation, or the flow of water through soil, to postgraduate students. And I designed this experiment using one of the pieces of apparatus in our teaching lab. This is a rigid wall permeameter. We've got manometers coming out at the side, connected here to these standpipes, where students can read the total head at various points along the side of the rigid wall permeameter, and then get an understanding of the relationship between this gradient and the flow rate, which they can measure. We have the flow coming through from the bottom, and then they can use a timer and a graduated cylinder to measure the flow coming out of the top. But the thing I realized, more than 10 years ago, is that it's quite interesting to put two different types of sand into the rigid wall permeameter, a coarse sand and a finer sand, and to then ask the students, where is the flow fastest? And this really flummoxes them, because intuitively, a lot of them want to think about flow in the individual pores, and they recognize that these pores in the coarser material is more open compared to the cores in the finer sand. But yet they have Darcy's law, and they're unable to take Darcy's law intuitively and apply the principle of mass conservation to realize that the discharge velocity is the same in both layers. They really struggle with that. So intuitively, this macro scale description using Darcy's law, when students are forced to really think about things, it starts to break down. But one of the problems that's really important to us in soil mechanics at the moment is internal instability. And a lot of my research over about the last 10 years has looked at this problem from the perspective of the individual grains. And the issue of internal instability is that if you've got a sand, and this is a cumulative distribution plot of particles in a sand that is gap graded. So we have a mixture of larger particles and finer particles. And if we take that rigid wall permeameter that I showed you a minute ago, and we put in a gap graded soil into it, we will see that at very low hydraulic gradients, you start to see the finer particles being washed out and the coarser grains being left behind. Now, this is a major issue for dam design and also for the design of flood embankments. And ICOLD, the International Commission on Large Dams, has recently issued some bulletins on internal erosion. And there's been a number of workshops involving the UK Environment Agency, the Corps of Engineers, and other European bodies looking at this issue because it affects the stability of flood embankments as well. And the reason it's such a big problem is once you have this preferential erosion of the fines, then that area of your dam or the foundation to your flood embankment has a higher permeability, it attracts more flow, and you can start to get a progressive erosion of the material. And this can threaten the integrity of your dam. And the most famous case study involving internal erosion is the near miss at Bennett Dam in British Columbia in the mid-1990s, where they discovered a major sinkhole caused by this. So these problems have real significance for our embankment dam and levee infrastructure. So that's why I think we want to be able to look at flow at the pore scale to aid our students' understanding of these phenomena, and then also to advance understanding and improve our ability to predict instabilities such as internal erosion. So I'm going to talk about some experimental work carried out by a PhD student called Howard Taylor, and numerical work carried out by a PhD student called Chris Knight. Howard spent a number of years in industry before doing his PhD, so he approached this from a very applied perspective, while Chris was a physicist and looked at things from the perspective of a physicist. So two very different students, but looking at the same problem, and their two perspectives I think are quite interesting. So this is a photograph of the apparatus that Howard used in the lab. So he took a sample of sand and put it into a standard triaxial apparatus, consolidated or compressed it to a particular isotropic stress level, and then he impregnated it with an epoxy resin. So an epoxy resin was drawn up using a suction through the sample in order to glue the particles in place. He then took a subsample of this to a materials micro-CT scanner, and he used a scanner based at Queen Mary University, which is also in London, just a ride away on London Underground. And he put his sample between a source and a detector. And this sample was rotated in a controlled manner. And for every about 1 degree of rotation, a radiograph was taken. And so a radiograph is the kind of X-ray image that's recorded when you break your arm. But by taking these large set of radiographs, where the sample is rotated in a controlled way, we can get a 3D image or a tomograph of our material that allows us to look at the pore space in 3D. And Howard looked at different sands with different coefficients of uniformity, or rather, I should say they're the same sand, they're both latent buzzard sand with different CUs. And a CU of 3 means there's a broader distribution of particle sizes within his sample. And he also looked at some glass ballotini with a slightly different particle morphology. And Howard took subsamples from these scans and used them as input to a CFD analysis. And in order to do that, he looked at the gray scale of the images and decided which gray colors are associated with the particles and which gray scale is associated with the voids. So he did what we call a binary threshold to segment the void and the particle space, and use that as input for his CFD analysis. So he did his binary image. He used a finite volume mesh within the image using open foam and solved the Navier-Stokes equations to get an understanding of the flow within the individual voids or within the pore space. So he simulated, in all cases, a laminar flow scenario where there was a pressure gradient applied across his sample. On the surface of the individual grains, he applied a no-slip condition, and he used a symmetry boundary on the vertical sides, and then flow moved downwards, as I said, under a controlled hydraulic gradient. So we have a controlled pressure gradient here. And from that, we can get a map of the distribution of pressure within the void space and also the velocity of flow. And I think that this kind of approach to solving or to looking at flow within a porous media is where we need to go to really understand these issues from a soil mechanics perspective. Howard did some verification by carrying out some experiments in the lab where he did permeameter tests within the lab. And he confirmed that his lab results were reasonable when compared with the CFD results. Acknowledging, of course, we wouldn't expect a perfect match because you'll always have some boundary effects within the lab that would not be evident in your small subsample that were considered in the CFD analyses. And then we now can go back to the MSc students and start talking about flow and show them that what we have within our soil is a distribution of velocities. And if we look, say, for example, in the solids line here, this is our velocity in the Z direction. And there's a wide variety within the pore space of velocity in the Z direction. We can work out our discharge velocity just as the flow per unit area, where that area includes both the voids and the particles, and our seepage velocity. And what we typically found was that our seepage velocity, which is the discharge velocity divided by the porosity, was always pretty close to the median of these local velocities. And here we can see that if we divide our velocity in terms of magnitude by the seepage velocity, we get, for all the different samples that Howard considered, when we look at the value of 1, that's close to the median value of our velocities. And as well as differentiating between the particles and the void space, Howard also came up with a way to look at individual voids and rationally decide where one void begins and one void ends. And to do that, he used watershed segmentation. And that is based on a distance map. And here we're showing it for how you would separate two touching particles using micro-CT data. So every voxel within the particle is the distance of that voxel to the edge of the zone where there's a change in the phase from particle to void is measured. And that distance can be viewed as a topology. And using the mathematics of watershed segmentation, we can identify which are the voxels associated with each particle, and then rationally decide where the boundary between the two particles is. And that exact logic can be applied to the void space. So we can identify individual voids and the boundaries between the voids. And along these boundaries, we can look at the points along the boundary between two voids that are furthest from particles and say that these are our constrictions. And this is the point where we would imagine the flow will be the fastest, but it's also the point at which the largest particle can get through the void space. So the size of these constrictions, or these local maxima, determine the size of the biggest particle that a given sand can filter. And that's an important concept in dam design. But we can also take the output from the CFD analyses and look at the local maxima and the fluid flow. And these are also associated with the constrictions. And we found that the locations of the geometric constriction and these local maxima and the flow were consistently very close to each other.
And then your time is up in less than a minute.
Thank you. And we can trace streamline through the flow, and we can see that where we get the biggest head loss, or the biggest gradient in head, is associated with these constrictions. Chris Knight, who's the second student I spoke about, he created his samples using DEM, and he simulated the flow around them using the immersed boundary method. Again, he's doing direct numerical simulation, but using the immersed boundary method to enforce the boundary conditions at the surface of the particles. And again, he traced streamlines through the void space. He looked at where his pressure gradient was the largest, and using a triangulation-based approach to partition his void space, again, he found that where he had his constrictions, that is where two voids meet, that's where he gets the biggest pressure gradient. So by doing this sub-particle scale simulation, we're starting to get proper insight and confirm our hypothesis that actually underlies the Kozeny-Kármán equation. So I think this is really important. The other thing Chris did was to look at drag on the individual particles. Now, our current understanding of the fluid particle interaction force is really based on observations of flow through monodispersed packings of particles. Chris was able to work out the force on his individual grains. And here we're looking at the force normalized by Stokes drag. And we can see that the force on the particles varies with particle diameter, as we see it coming up here, and it also varies with packing fraction. These equations based on the monodispersed packings, they don't accurately capture the forces on the individual grains. They underpredict the force on the large grains, they overpredict the force on the small grains. And that's really important because if we want to simulate movement of particles using what we call unresolved CFD-DEM, we need to know these forces accurately. And I think this is an area of research we really need to pay attention to in soil mechanics. And we really need to develop our ability to accurately measure, model and predict drag if we're going to look at the kind of issues I was talking about at the beginning, such as how flow heterogeneity can start to cause erosion and flood embankments. And we've been looking at different approaches to determine this in a computationally efficient way. We've been developing approaches based on Voronoi tessellation. But the key to developing these approaches that will allow us to go forward and make accurate predictions is having this information of fluid flow at the subparticle scale gained through solving the Navier-Stokes equation. So when we're looking at flow at the particle or subparticle scale, it's heterogeneous. Darcy's law doesn't reveal the fundamental physics. We hit that pretty quickly, as I said, with the students who start to get flummoxed when they think about flow from one sand to another. When we have these DNS simulations, we can get the data that we need to really understand at the particle and subparticle scale, the flow around grains and the interaction of that flow with the particles and the forces that can lead to instability in granular materials. So thank you, Chloe. I think I should stop sharing now, shouldn't I?
Yes, please. Thank you, Catherine. So Benoit, the floor is yours. To be fair, I'll give you a little more time to make your argument since we went a little over.
Thank you very much, Chloe. Let me share my screen now. Okay. Okay, do you see the screen, right?
Yes, perfectly. Yeah. Thank you.
Okay. So first of all, good morning or good afternoon, everyone. So yes, so look, long story short, as you will see, I'm against the argument, and I'm going to try to bring the what I would call the physicist view, but it's not only a physicist view, it's actually more like I would say a microscopic picture behind a Darcy law, and I hope I will convince you that in contrast to what was just said, I do think that Darcy's law is meaningful for flow within individual poles. So, okay, let me start. It's basically more or less the same definition as what Catherine gave, but I think it's important that I use my own words. So, as was said by Chloe in the introduction, Darcy's law, from a physicist point of view, is simply Onsager phenomenological law for transport. So it means that it relates the flow rate to the pressure gradient, which is the driving force that actually induces transport. And for me, the complexity, if you like, is what do we put here in these prefactors? So usually, from an engineering point of view, what we do is we assume that we have two parameters here. So K is the permeability, so it's in square meter because it's actually a cross-section area that conducts the flow, and eta is the viscosity because this is what resists the transport resistance of the flowing liquid. So usually we assume that we have these two parameters and that we can simply take the bulk values. I mean, one is a material constant, K, and the other one is a fluid constant, and we just put them together, and then when it doesn't work, basically, when it doesn't capture the exponential results, we say, okay, it's a failure of Darcy's law. But for me, it's not actually a failure because there's a strong background behind this Darcy equation. I mean, it's usually introduced like this as a sort of, as I said, a Onsager equation, but it's actually, you can simply rederive Darcy law starting from the well-known example of Poisson flow. So in Poisson flow, you start from Navier-Stokes equation, which is basically a momentum conservation equation. And you assume that you have a laminar flow, so you can neglect these nonlinear contributions. And you simply have to solve this equation. If you do for a simple geometry, like a slit pore, cylindrical pore, you end up with this parabolic profile that we all know from our textbooks. Now, usually, I mean, with the advent of nanofluidics, we realized something like 20 or 30 years ago that in some cases, the non-sticky boundary condition that we all use here might be not relevant, and sometimes we can have slippage. And if you have slippage, you can explain, for instance, the large flow that have been measured in the carbon nanotubes, for instance. But again, my point here is that you see that from a very fundamental physics equation, I can rederive this Darcy equation. And in this case, it's well known that the permeability for a cylindrical pore is the pore size to the power 2 divided by 8. And again, I mean, from a physics point of view, the simple scaling here tells you that when you have a porosity of an average size D, somehow the permeability should scale as the pore size to the power 2. There are well-known limits to this linear equation, Darcy equation, okay? I don't want to go too much into the detail because I don't think it's really part of the debate, but it's important to consider the well-known limits. So a well-known limit, first of all, is compressibility effect. So when you have a large Mach number, so the Mach number is simply the ratio of the flow rate to the sound velocity in your system. So what it means is that when this Mach number is large, it means that as the fluid is moving inside the material, it's actually producing a pressure wave, a compression wave. And for large Mach numbers, this pressure wave is actually affecting the fluid. But in most liquid applications, we're usually at small Mach numbers, so it's not really relevant. The second non-limit is the non-linearity. So for instance, if you have a gas, if you have a small Reynolds number, well, typically you remember in the previous slide, I said, if you can neglect the nonlinear term, you end up with Darcy equation. But of course, if you have turbulences, if you have this convective term in Navier-Stokes equation, it is no longer valid to simply assume that the flow rate is proportional to the driving force. And you have this extension, which is known as the Darcy-Forchheimer law. Okay, that was well-known limits. So now let me move to the topic, the important topic. If we go to the pore scale at a very small scale, okay, the molecular scale, what can we say about Darcy's law and its validity? So again, you remember what I said. Usually we assume that K is a constant, an intrinsic constant of the material, and eta is an intrinsic constant of the fluid. So we did some simulations on alkane transport into this disordered porous carbon, which is a realistic molecular model for kerogen in gas shales, okay? And this is what we get. So it's the flow rate normalized to the driving force, okay, as a function of 1 over the viscosity. So what we have here is data for methane, propane, hexane, nonane, and dodecane, okay? So increasing molecule size. And you see that, so the dashed line is actually the prediction from Darcy equation with a cylindrical pore. So first of all, it is not good, but you see that the order of magnitude is correct, right? If I take the pore size to the power 2, it's not so bad. And even if it's a strongly disordered material. Second, what we see is that the permeability, which is in fact the slope here, you see, it depends on the fluid. And even for the same fluid, you see methane, for instance, it depends on the density of the fluid, because the density of the fluid inside the material changes the viscosity, and this changes this prefactor that here we have here. So basically, the conclusion of this slide is that the linear relation between the flow rate and the pressure gradient still applies, and actually, even in strongly disordered and nanoporous materials, where you could expect some molecular effects to make the Darcy's law invalid, it actually works super well. The only problem is we don't know what to put for the viscosity and for the permeability, and this is where your trouble starts, in fact, that we don't know what we should put in there, but there is some physics. It's just that it is not obvious what physics we should put in these numbers. So I don't want to go too much into the detail, but you need to understand that this, the fact that the permeability depends on the fluid and it is no longer an intrinsic property of the material is actually something you can predict, because as I said, Darcy law can be re-derived from Stokes' equation, where you neglect again the turbulence, I mean the convective part. And if you solve this equation in the direction perpendicular to the driving force, so you get rid of the pressure gradient, you solve this in Fourier space, and you predict, and that's a very important hydrodynamic result, that the Fourier component of the flow rates, the time correlation of this Fourier component, should decay exponentially with time. And when you look at these time response functions for again fluids in strongly disordered and nanoporous materials, you observe that you have a complex behavior that does not match this simple viscous flow hypothesis. So basically what I'm trying to say is that, again, Darcy law has a linear response between flow rate and pressure gradient applies, but it's just that the permeability, because you have this non-viscous, this complex behavior of the confined fluid, becomes a complex quantity to predict. And in fact, if you want to understand in very simple words, you can consider the following argument. So in fact, here in this equation, which is a macroscopic equation or mesoscopic equation, you actually compare two quantities. This is the momentum transfer, and those are the different forces applied to the fluid particle. And here, this term is the stress relaxation, it's the viscosity contribution, okay? So when you use this classical mesoscopic equation, what you do is actually to assume that the time scale it takes to transfer momentum between fluid particles is extremely long compared to the time scale it takes to relax the constraints within the fluid particle, okay? So, as I said, the viscosity, we know from statistical mechanics that it's directly related to the stress correlation function inside the fluid. For most liquids at room temperature, we know that the typical relaxation time is of the order of 1 picosecond. It is extremely fast from an engineering point of view. For the momentum transfer, and that's related to this Fourier component contribution that I discussed before, we can predict from this exponential term that the typical time scales like this. So that's the fluid density, that's the viscosity, and K is the wave vector over which you're transporting your fluid particles. So when you do classical hydrodynamics, by construction, it's a macroscopic theory. So you're looking at small wave vector, meaning large distances, macroscopic distances. So in this case, you see that indeed, tau becomes extremely large compared to the typical relaxation time within the fluid particle, okay? But when you confine the fluid in a nanopore at an extremely small scale, you see that K, which is typically of the order of 1 over the pore size, K becomes very large, so that this time scale becomes comparable with this. And this is the breakdown, this is what explains the breakdown of the viscous hypothesis used in Darcy equation to use a constant permeability. So what I'm trying to say is that when you reach this pore scale, this very small pore scale where the molecular nature of the fluid matters, you actually have a relaxation time of the stress and a momentum transfer time that become comparable, so that you have memory effects that explains why your permeability becomes fluid dependent. How much time do I have left, Chloe?
You still have about 8 or 9 minutes.
Okay. So what can we do with this? So I just told you that there's a sort of split between K, that would be a permeability of, a constant of the material, and eta, that would be a fluid property. We just saw that it doesn't work, right? If I transfer my data from methane to a larger alkane, even if it's the very similar chemistry, it fails, right? I showed you a quite convincing example, I think. So what can we do? Well, hydrodynamics, because of what I explained, these memory effects no longer apply. So we have to switch to a different formalism. And for this, we can use statistical mechanics, which also predicts transport coefficients. So typically what we do is to replace this, these two parameters, permeability divided by viscosity, by a single constant that I call permeance. I know that it depends on the field, but for me, here I call this the permeance. We have to agree on this. And I cannot go into the details, but believe me, it's an exact result from the fluctuation dissipation theorem in statistical mechanics. It is directly related to the collective diffusivity. And it's easy to understand, right? That the permeance is not a self-diffusivity property. It's a collective property because it's all molecules moving together through the material. So this is an exact result, okay? And actually, this collective diffusivity, so it's the way all molecules diffuse together, if you prefer. And one of the important contributions is actually the self-diffusivity, plus all these cross terms, which you see involves the correlation between the velocity of molecule I and the velocity of molecule J. So it's clearly cross terms. It's hydrodynamics interaction. It's the fact that when one molecule is moving, it's actually creating a flow, a velocity field for the other molecules that move with this molecule. So now when you work with extremely small pore, like nanoporous materials, what I'm going to say is not a general result, okay? It's really because we have extremely small pores. But one thing that is nice is you can see that the collective diffusivity actually is quite close to the self-diffusivity. But this is due to the fact that when you have an extremely small cavity, if you have one molecule inside, it is not too much affected by the cross terms, right? Because most molecules interact mostly with the surface and not really with the other fluid molecules. And you see that's why this approximation that the collective and self-diffusivity agree gets better as you consider large molecules, because inside the same cavity, you can put maybe 1 or 2 dodecane molecules, but you can put a larger number of methane molecules. That's why we have more pregnant cross terms for small molecules, okay? And the good thing is, once we have, if we can use this approximation, it's good because we actually have a lot of statistical physics model for the self-diffusivity. So if you agree with me that the collective and the self-diffusivity are close, I can use a model for the self-diffusivity, use it for the collective diffusivity through this approximation. And with this, I can predict the permeance of my porous medium. And this is just to show you an example. Again, it's a different snapshot, but it's the same disordered porous carbon that I showed before. And just to show you what kind of, like very fundamental physics we can do with this, we looked at the diffusion again of the different alkanes that I mentioned before into this disordered nanoporous material. And we tried, to be honest with you, we tried different theories, okay? But we found that there's one that works quite well, which is the free volume theory that was developed in the, I think, in the 60s for polymers. And the way it works is very simple. You assume that the self-diffusivity of the molecule inside this material, it's the self-diffusivity of a single molecule, so infinite dilution regime, times this exponential term. And so V mol is the molar volume occupied by the molecules, and V free is the volume of the free cavities in the system for diffusion. So basically, you assume that the molecule will diffuse because it finds around itself a cavity to jump into. And again, I don't have time to go too much into the detail, but it's nice because actually the molar volume is directly related to what I call gamma, which is the number of molecules inside the system. And the same, you see that when you add molecules into the system, it's directly related to the change in the free volume. So when you have 0 molecule, you have a porous volume, which is related to the porosity. And as you keep filling the porosity, of course, it decreases the free volume accessible. So you see that this simple model predicts, based on statistical mechanics, that the self-diffusivity should decrease with the number of adsorbed molecules in the system. And as you can see here, I show you this permeance, K, which is this proportionality factor, as a function of the free volume in the system. So here you have a small number of adsorbed molecules, large number of adsorbed molecules. And you see that for all fluids, you see, and different densities of confined fluid, we can nicely reconcile all this data into a single statistical mechanics model. So that's my conclusion. So I think for me, I mean, Darcy's law is actually a robust linear response model. And that's it. If you stick to this, I think it works, unless you put like crazy pressure gradients and then you start having non-linearity. And for me, it is clearly based on well-defined quantities. It's just that in complex porous media, because you have these strong memory effects that I mentioned, there's a correlation between the two characteristic times, the permeability of the confined material become intrinsically coupled to the properties of the confined fluid. And that's why it makes it a nightmare to predict from fundamental physics the resulting permeability inside the complex porous material. And typically we have these non-viscous effects that appear, but I want to insist, okay? I said that it's complicated to predict the permeability, but I didn't say that the equation fails. It's just that you don't know what permeability you should put and how it depends on the fluid density, etc. But my conclusion is that if you take all of this properly into account, clearly Darcy's law is a meaningful, even to predict flow at individual pores in complex material. And with this, I thank you for your attention.
Thank you, Benoit, so much. I'm anticipating that the vote will be difficult. So now we'll open the floor for questions. If you would like, Benoit, you can unshare your screen.
Sure.
So the floor is open for questions from the audience. So if you would like to speak, feel free to activate the raise my hand button at the bottom right of your screen, or feel free to use the chat box. I see that France already has a question. So France, feel free to go ahead.
Yeah, so first of all, thank you very much, Catherine and Benoit, for your presentations and for introducing us to this complexity. But, and now comes the but, you have to give us a little bit more. And let me be more specific. Ben basically told us, okay, if there is a time relaxation time, which is much greater than, no, much smaller than this other characteristic time constant, then you can apply hydrodynamic and you can separate permeability and viscosity in order to make the prediction. So you basically make the case, you just tell us at the very small scale when to separate and when not to separate, while the linear response theory remains valid. So basically what you're telling us, at larger scales, we should always be good with hydrodynamic. But then we come to Catherine, who tells us exactly the opposite. When she goes to the pore size of micrometer pore size, well, Darcy's does not capture the physics. So can you try to help us a little bit? You know, how do we bring that two things together? Because otherwise it becomes a vote, she said, he said. So thank you.
Catherine, do you want to start?
Yeah, I mean, I think we're coming at it from very different perspectives too, which probably complicates, you know, being able to see from which side of the either side of the debate is more valid. I mean, to be honest, at the moment, I couldn't say this in my debate because, you know, I had to adopt a certain perspective in speaking. You know, we're trying to develop network models which effectively are using Darcy's law at the scale of the pores to describe the fluid flow from one pore to another. But the problem when you're using those networks models is that what we can see at the moment is if you use some kind of rational geometrical approach to define your conductance, which is what you would use as your input to Darcy's law, your permeability values are off from what we get through very accurate DNS simulations. So those network models, I think, have great potential, but we can't develop those network models without doing DNS to understand what conductance we should use. So while I can see, in a sense, from my perspective of looking at seepage as a geotechnical engineer, that at the particle scale, these poor network models that use Darcy's law and have a conductance to describe the flow from one void to another have got a real benefit, we can't develop them without the DNS data to confirm that those conductances we're coming up with are correct. So I don't know what
Catherine, can I just ask you here, are you sure that in your DNS simulations, you capture the right boundary conditions and everything, you know, that this becomes really physically representative of the phenomenon?
That's a very good question. And I was limited in the data I could show here today because I could really only present published data. So we have data that was gained in collaboration with Elizabeth Bowman and Nicoletta Sanvitale in Sheffield. They were working with myself and Buddy Zhao at Imperial. And what they were able to do was to use tracer particles in the fluid with transparent soil and experimentally measure the fluid flow in a subvolume. Buddy, who is working with me, Buddy is now in UCD in Ireland, he took the 3D imaging of that subvolume that we were able to acquire through controlled movement of a laser and took that as input to a DNS. And we found that the boundary zone where our model did not agree with the experiment was very small, maybe 1 to 2 particle diameters around the edge of the cube that, or sorry, it wasn't a cuboid that we simulated. So I agree. I think we need to look carefully at how accurate these methods are, but the data that we have using transparent soil indicates that they're pretty, the rational boundary conditions that you can assume, they're only affecting the overall fluid flow within a very small region close to the boundaries.
Can I say something about this? Yeah. So I mean, I have to be fair. I think Fran's question is good, and I think what I'm going to say is going to be a disappointment for him and for the audience. But if I try to summarize what I said that there is physics, because that's part of the debate, and I said that there is a mean to measure the permeance through this collective diffusivity, which is great, right? Because it means, for instance, in neutron scattering, if you use deuterated water, for instance, you do get directly D0, and that's actually what we're trying to do in my research group. So it's good news, but then, I mean, the disappointment comes from the fact that I'm not really answering your question, Franz, because it's like you measure this collective diffusivity by different means. It's not a permeability experiment, but then I'm just saying that basically, okay, you get directly the permeance, but I haven't answered your question, which is how do I predict it? Because it's like I measure it indirectly, which is nice, but still I cannot predict it. So I have to be fair. And at this stage of the debate, I would say, I am not in a position to, as a physicist, to tell you, okay, look, do this, take your sample, and that will work. That's why in the engineering field, you keep using these finite element methods, which are fine. But honestly, I have some serious concerns because you see, the problem is you do this DNS, or I mean, you do simulations with very nice tomography data, but you just assume that what you put in the equations holds, right? So it means that if I give you, for instance, a sample for which I know that they fail, then it's going to be a big failure, right? Because you're going to predict something. And the best example, I'm sorry, because it comes from a completely different field, but I think we all heard of this example, carbon nanotube, right? If you take, I mean, carbon nanotube, normally you agree that the Poiseuille flow should work, right? It's the perfect geometry. Even this, you can predict, if you do like, you solve Navier-Stokes equation, you get the Poiseuille flow, which is trivial. You get a permeance that is wrong by orders of magnitude, just because we ignore all the interesting physics, which in that case is slippage effect. So it's not, I mean, it's interesting, but we can probably think of fancier effects. But you see what I'm saying, Catherine? I think that, okay, as a physicist, I'm saying things, but I'm not really in a position to give you answers, practical answers. But at the same time, the engineering approach, which is nice because it's robust, relies on very strong assumptions. I do think that in many cases that are of interest, these approximations are just not okay. And I'm sorry, Franz, because I know that I'm not really.
No, hey, Ben, my deception is endless, but I'm happy that you said it honestly. I never wanted a physicist to design my house, you know, as a civil engineer. Don't worry about that. Thank you very much.
I believe Zdenek has a question.
Yeah, I wanted to make a comment from a somewhat narrow perspective of hardened cement paste or concrete. Actually, I think all the presenters have made excellent presentations which are right and valid in a certain sense. But I think the key to the differences is the pore size. And extreme of that is hardened cement paste where mean width of the pores is 1 nanometer. Now, in those pores, of course, Darcy's law or even pressure difference does not matter, because water molecule mean free pass is 70 nanometers, and there is no chance that pressure would affect the permeation. The problem is that of statistical diffusion. It's best characterized by Fokker-Planck equation, which has a diffusion term, statistical, and which is a gradient term. Now, how do you explain that permeability apparent, okay, of cement paste goes down by 2 orders of magnitude, 50 times, as you decrease the humidity? So in that case, everything depends on the creep of water molecules along the adsorption layers filled pores. Now, that of course happens. Our data are for unsaturated materials, but it's surely true also for saturated case. And then actually the good theory does not exist for this on the physical sense. We have equations which work on the broad scale. So it's sort of a narrow perspective that I'm presenting, but should be considered, I think.
Thank you, Zdenek. Benoit and Catherine, maybe you would like to follow up with this.
I don't really feel well placed to comment on that, because I've never looked at flow at the subparticle scale, at particles that are that small. I've never looked down at the nanometer scale.
I think if I can add something to this, I think it's a great comment. You know, part of the complexity comes from the fact that we do have a lot of theories, and I say a lot, it's a lot of theories for self-diffusivity. You know, I mean, this free volume theory that I mentioned, they are quite robust, even this intermittent Brownian motion, etc., which accounts for adsorption effects. The problem with Darcy equation and the fluid flow problem, sorry, is the fact that we don't have a robust theory for collective diffusivity and therefore for permeance. So for instance, as I said, I mean, we're working on this with some students, and one thing that actually struck me is the fact that we couldn't find a simple theory except maybe what is known as a De Gennes narrowing. Okay, so De Gennes narrowing is a very complicated, it's not very complicated, but what it predicts is that if you know the structure factor of your fluid, so the structure factor is what you measure with the X-ray diffraction, for instance. So it's really the density fluctuations in the system. Okay, so for a crystal you get Bragg peaks, but for liquid you also get correlation peaks. And what De Gennes predicted, it was actually in polymer science, is that if you know the structure factor, you can show with a simple model that the collective diffusivity is inversely at a given wave vector is related to this structure factor. Actually, it's inverse structure factor. And that's a nice theory. So we started to look into this because we thought, well, if I can measure the collective diffusivity at a given wavelength, then I take the limit when the wavelength goes to 0, so infinite distances, so macroscopic transport. then I would be able to provide a value for the collective diffusivity and then for the comments. So we tried this, but in fact, this Gaussian narrowing is not, it becomes a kind of trivial close to at vanishing Q vector, wave vector, but it's let's say only valid close to the main correlation peak, which is not what we would call the permeance, which is again a macroscopic transport property. So again, what I'm trying to say is that we do have tools, we do have theories, but for the collective diffusivity and therefore for the permeance, we are not in a position to give you from these theories something robust that we could plug into a software, for instance, to do finite element calculations.
Thank you. Andrew has a question.
Well, I'd like to thank Catherine and Benoit for very interesting presentations. It does seem, I agree with Zdeněk, that the scales here are so different of what you're talking about. I'm also a civil engineer, as Catherine knows. when civil engineers start to say abandon Darcy's law, I mean, I sort of have the sense of heterogeneities and all the rest of it that you're describing. But I'm going to ask you, if you want to abandon Darcy's law, it says has no meaning. What do you propose instead? I mean, how do you propose to proceed at the macro scale that you started with when you talked about seepage through levees and macro scale phenomena like that?
I think that first of all, the kind of constraint of the debate is that we're looking at the particle scale. Isn't that correct, Chloe? I can't remember the word. Was it particle or pore scale?
Yes, correct.
So I completely agree with you, Andrew. We need Darcy's law. That's what we need to go and do our like hundreds of thousands of CW analysis of embankments like I used to do when I was a graduate engineer. But what we also need is the insight to understand how heterogeneity affects flow, to understand how layering affects flow. And from a pedagogical point of view, when you're teaching, the students do intuitively start to think about what's going on around individual particles. And I think to help their understanding, you know, a particle scale network model that uses some conductance isn't really going to help. It's being able to show them these images of how the fluid flow varies in the void space, to be able to talk about these issues, about this is where the head loss is occurring within the void space. That has tremendous value. So if we want to use Darcy's law properly and effectively as practicing engineers, and obviously my experience in engineering practice was limited. Most of my career I've been an academic, but I did work on a lot of seepage problems during that period in industry. And I think to underpin those people who are going to go out and do that work, this type of subparticle modeling using DNS is of more value than some kind of a network model that's using some kind of derived conductance.
Maybe I could say something about that. So first of all, yeah, I agree with Andrew that what else? I mean, because as I said, this Darcy equation is quite robust. I mean, when if you take it as a simple linear relation, you multiply the pressure gradient by 1.5 and you get a flow that is 1.5 larger. So again, for me, the question is more like, what do we put in the prefactor? And just to comment about what Professor Bazant said, I agree that there's obviously, we just did a jump of by 5-6 orders of magnitude in terms of pore scale, but I used nanoporous materials to illustrate my, what I wanted to, my message. But I want to insist that these adsorption effects that are obviously more than pregnant in nanopore, there are also well-known examples in macroscopic media where they do matter. For instance, if you take the distribution of pollutants or a scattered fluid inside a flowing liquid, we know that this retention effect, adsorption effect at the surface of the large particles also matters. And the best example is actually chromatography. Because when you do chromatography, you actually separate fluid by inducing let's say a Darcy-like flow. And you have all these adsorption effects which are coupled with the flow rate. So, I mean, the reason I want to insist on this, it's because I don't want people to think that what I said is only applies to a strongly disordered material. I mean, it was more like to illustrate my message, but I think that there are, for instance, with the ionic species, when you have charges, electrostatic charges, we know that the interaction, which is given by the Debye length, can exceed by far the pore size. You can have the Debye length by, let's say, 100 nanometers. So it also applies to let's say, more classical porous materials, I would say.
Thank you. Any other questions? Yes, Franz has another question.
I just actually wanted to make a suggestion on a question. First of all, Ben, you showed us from the nanoscale that you use the velocity correlation function, cross correlation function, in order to determine this prefactor. Is there a way of, I mean, the application of these statistical physics functions are not limited to the nanoscale. You can apply them whatever type of scale. Wouldn't it be, so let me ask you the question, can you apply them at the scale where Catherine is working? What I mean by this here, can we make a handshake in methods in some way so that we identify sort of the difference given these fantastic experiments which she has with her colleagues in order to identify, you know, what is that prefactor? Can that prefactor, if it was treated in the context of velocity correlation, velocity cross correlation, can provide us insight where the separation of permeability versus viscosity of a fluid can be applied?
It's a good question. I mean, that's exactly what we should try to do. I mean, to agree on a set of materials, and so not to, again, to be fair. The problem, if you like, is usually the way people measure the collective diffusivity is by using permeability experiments. So you're not helping, right? You're just it's just closing the circle. So what you could do is, I mean, at least in theory, okay, is if you do again neutron scattering, normally what you get is because I mean you have to use deuterated water, for instance, because deuterium has a strong coherent cross section for neutrons, and that means that basically what you see is the cross term. So you see the collective diffusivity, and for me that would be great to measure the collective diffusivity because that's these time response functions that I described. This is what you measure. You measure D0 as a function of Q, Q being the wave vector corresponding to the fluid particle displacement. So again, if you take D0 when Q goes to 0, so infinite distances, you should get the permeability. And that's the point, but it's just, I mean, to be honest, we all work in quite different fields, and it's kind of difficult to find time to sit and agree on materials and what we do. And also, to be honest, neutron experiments, you have to go to a special place. I mean, it's not something you do in your lab, right?
I would like a brief comment, if I may. You certainly hit the right points, and the main difficulty actually with some very small pores that we cannot do properly direct measurement of permeability. It's inferred. We have to reduce it from non-steady states. And then, of course, what to put in. So, in my opinion, actually you have to work with Fokker-Planck equation on a small scale. Distinguish statistical diffusion, which is independent of pressure gradient, which is mixed together with Darcy type flow where pressure gradient does matter. That's the principal difficulty. So you need to assume a model, and then you retroactively, by fitting data, you determine what's happening. But of course, it very much depends what model you assume. What we are seeing in these very small pores, it's true of shale as well. And then we have only macroscopic experiments, and we cannot measure really this permeability directly. At least I don't know. Maybe somebody has found out how, but I'm not aware of it.
Yeah, I actually had a follow-up question about this. It seems that the crux of the matter here is that you cannot measure something that you don't assume may happen. So you have to have a certain knowledge of the physics that may be ongoing. So how do you go about detecting emergent phenomena? Do you have any exploratory simulation tools or experiments that would allow you to actually say that this is an unknown phenomenon that you have to actually capture and go about this?
It's a good question. It's a very good question. Yeah, because it's no, it's again, it's more like a sort of closing circle, like because usually we know from like simulations what should be the normal response of your medium. So for instance, you simulate finite element methods and you get a flow response. And again, as Andrew said, usually you feed this against the Darcy equation and you get a permeability. So usually what we do is we compare with what it should be. For instance, if you have no adsorption effect. And then you say, oh, I don't get the same. So maybe we have adsorption effects, or let's say I speak of adsorption, but it could be something complicated like these memory effects that I mentioned. So it is complicated to answer this because it's not something that directly come out from your experiments. Like even, for instance, I mentioned these neutron scattering data. It's not like inside the data that you see the signature of adsorption or not. So yeah, you need to think of some complementary experiments that tell you exactly if you have this kind of effects, but it's usually not what is done in the literature.
What do you both think about the use of machine learning to try to highlight some emergent phenomena? Have you seen anything published about this?
I haven't seen anything published, Chloe. I guess the issue, I don't know if you're talking about machine learning to correlate some particle scale characteristics of permeability or something. Is that what you mean?
For example, I actually read a paper by Wei-Ching Sun lately. He did not apply it, I think, for topology related to permeability, but he had some topology parameters that he could involve or not in a plasticity law. And then a neural network actually decides what combination of parameters should be included or not. You don't completely go away from pre-assumptions because you have to inject nodes inside of a graph of decision, right? But it randomizes a little bit. So I was wondering if anybody thought about deploying these methods to explore those fields as well. It's somewhat experimental. It's numerical, but it's still very experimental at the end.
Yeah, look, everything helps, right? So if we get some insights from machine learning, I'm not against it. It's just that, again, that's related to the last part of your message, which is if you use some tools, if it's numerical, then of course be careful because what you get is the machine learning, and it's the take-home message from something with hypothesis in mind, right? So it means that in practice, what you would have to do is to do experiments. But I think I like the comment because I'm not too much into machine learning actually, but okay, but my sort of personal opinion. But no, why not? I mean, it's going to be, that would be useful. For instance, what I would do is take same chemistry, same type of sample, try to change, just a few things. And then, for instance, we know that if you decrease the temperature, I cannot tell you, regarding your previous comment, Chloe, I cannot tell you in advance when adsorption is going to play a role, but I can tell you that if we're speaking of physisorption, if you decrease temperature, that becomes more important because it's an exothermal process, right? So what I'm trying to say is that you could try to get at least maybe not a model, okay, but a sort of very, very useful hint at the effect of adsorption and all this, because all these strong correlation effects, adsorption, but also what we call in nanofluidics molecular granularity. The fact that the molecules at the scale it's not a continuum, right? Yeah. The only thing we know is as you decrease temperature, of course, they become more important. And the same if you increase the density. So there's room for this kind of experiment. I'm just a little careful about using some because then again I insist what you get is the machine learning signature of the numerical model.
True. And I believe Zdeněk has a follow-up comment about this.
I would like to only echo what Benoit just said. And with regard to adsorption, what is essential is connectivity of the pores, which we didn't discuss. Again, from a narrow perspective, if you have a hardened cement paste, which has water cement ratios in old times 0.7 or higher, or 0.8, then capillary pores are percolate, they are continuous. If you go to 0.3, they are not. They are actually irrelevant for diffusion or permeability, because everything has to pass through these extreme narrow absorption pores. And therefore, connectivity of pores is a different aspect, it's not porosity. And that's, if you go to small scale, that's essential aspects. Which pores, which size of pores connects, what are the narrowest passages which really control the diffusion.
Right. Thank you for this. Well, I think our time is almost up. This was all very rich conversations from very different perspectives. It seems that there is still room for discussion, so please feel free to continue discussing during the break times and beyond, if you would like to. For now, I'd like to switch to the last part of this debate, which is an interactive voting process. You will see in the chat the information that you need, and I see that SA just pulled out the information. So the idea is to go to this website, paulev.com, and then enter the name of, for this conference, Biot-Bazant CO 685, and then you will see some questions appearing on your screen, and you'll have the possibility to vote, and we'll display the results of these votes as people log in. So I'll give you 1 minute or two to log in, and then we'll get started. Okay. All right, so this is the first question that, for this debate. Is Darcy's law a good inspirational model to find relationships between field variables, or is it a misleading relation? So please vote. It is an inspirational model. It's somewhat useful, it's partially misleading, or it is a misleading relation. Please vote, and we'll display the polling results. Right. People still think of Darcy's law as an inspiration, apparently. All right, it seems that we reached a plateau here. So I can tell that Darcy is still quite popular, with 51% of the people voting, saying it's still an inspiration. Some things never get old. Let's switch to the next question. Okay, is pore fluid flow a research question for academic to address, or a problem for engineers to solve? So what do you think? Academics, engineers, or both? Yeah, that was an easy one, I think. Though some academics still want control. Okay. All right, I think we plateaued again. We have one last question for you. Let's move on. So do you think that the topic that we discussed would be nice to see in a review paper? Yes, no? What do you think? right. I think that the results stabilized again. So we have a majority of yes. So Benoit and Catherine, you know what's coming next, huh? So we will actually be in touch for what's happening after the conference. I think that closes the event for this debate. Oh, you okay? I didn't know that. There's an additional question. I think you're actually voting on the motion. So wait a second. Please tell us what you think. Is Darcy's law actually indeed meaningless for flow within individual pores, or is it not? What do you think? Okay. Okay, so I think we're still moving, still moving. Okay, so I think we have a majority of people think that Darcy's law is meaningful, even within individual pores. So that leads us to an interesting discussion. If there's a review paper, the goal is, the rule is that the winner of the debate starts with the first draft. So I tell you that, Benoit, right away. So no, more seriously, this was a very lively and interesting debate. I really want to thank both our debaters who make an excellent job presenting very different perspectives, very well documented and very well articulated and argued. And thank you for the participants to be with us, whatever the time is where you are, and participating in these very interesting conversations.